Started with ThrustMIT. So I guess yeah. So if the so if you guys want to, I guess, sort of get started by telling us a little bit about your. I mean, I have all of your documentation in front of me, but if you want to get started by telling us sort of what you think is interesting about your rocket.
All right. So basically, where we are from, rocketry is not such a big thing as it is in America. And the one of the main mottos of Trust MIT is basically promoting rocketry in India. We feel like there's a huge opportunity over here due to the craze of students and the way students like to build things and all over in India. Right now, we are more like the general population is more towards automobiles and all, but we want to bring that out to aeronautics and further into rocketry and all. So that's basically our one motive. And second one is we like to do research as a team, and we like to make new stuff and make all of it ourselves, keeping commercial off the shelf stuff as minimum as possible. So that's the second motto of our team, and we build the rocket based on that one, and second based on our past experiences in SA Cup. One of them is the 2018 SA Cup, where we had a fin failure and we couldn't reach the target apogee. And second one was 2019 SA Cup, where we have a commercial failure of the motor, and due to that we had a body tube failure and again could not reach the target apogee. So our basic idea was actually learning from those mistakes as well as building upon them and taking our rocket to new heights basically. So Phoenix is like rising from the ashes kind of stuff, if you will.
Yeah. Sounds good. Okay, so I've got a couple. I guess we'll start just sort of diving into the technical questions. So my first question is sort of from an engineering perspective. What made you? So first off, you mentioned the nose cone bulkhead.
Yes.
You WPC. What is that?
It's a wood plastic composite,
Oh, okay.
which is, yeah, it's readily available with us and it has a very good compressive strength. So we found it to be the best suited for our needs.
Okay. Yeah. I think you might have just missed that in your list of acronyms. So
Oh,
yeah,
all right.
yeah, I was just wondering. Okay, WPC. Not sure exactly what that was. And then the second question was, so I guess, so you went with 6061 T6 aluminum for
Yes.
your fins.
Yeah.
So um, what's the engineering rationale behind that?
So the basic reason for selecting 6061 aluminum was first of all, like I don't know if it's viable in America or not, but in India these things are very costly, metal alloys and all. And we wanted to find a cheaper alternative which did have the structural strength as well, and which was of course near to us with good machinability and workability as well. So we found 6061 fairly quickly and near to us, and in our tests and all we found it to be sort of very viable and the best option that we could use.
Okay. I guess so the question would be my question would be more along the lines of what did you see as its advantages versus materials like fiberglass or carbon fiber for the fins?
Yes, so we extensively use carbon fiber for our body tubes, and it kind of gets very expensive by the end of the entire manufacturing process. And like using materials like WPC, then MDF for molds, all these are ways of cost cutting as well as keeping the quality at a standard.
Yeah. Yeah. So the use of the use of 6061 aluminum over fiberglass or carbon fiber for the fins was primarily cost
Yes,
and ease
and
of.
yeah, and it did not even cost us much weight
Yeah.
in the aspects of fin attachment and all. And it's difficult to attach carbon fiber fins with the sort of body tubes and the internal structure we have going on.
Yeah. Okay. That makes sense. So what made you choose? I assume that you're familiar with some of the more, I guess, standard ways in which fins get attached to rockets, with things like basically with like through the wall fin mounting to the motor mount tube, and then epoxy fillets, and then maybe a layer of tip to tip fiberglass or carbon fiber. So what was your rationale for using this setup of with the aluminum fins and then held in place with bolts and and that stringer system?
Yes, yes. First of all, this question was also addressed by Tony sir to us about the fin attachment system. He was also very skeptical about our attachment system. And honestly, after the first failure in 2018, we really had to step up our fin game because we thought that normal methods won't just cut out. And we kind of went over the top in 2019 as well. We had uh, a brand new system of fin attachment over there. It is actually patented, like it's under the process, but we still haven't got it in patented. It takes a while. And the system we went for this year was along the lines because we wanted to make the system modular. So it had to have stringers. It had to have centering rings because the motor needs to be centered. And we thought, why not use both of these two? And instead of using some other methods to attach the fin, we use these two and get it done. And we found in our simulations and all also that this was kind of very practical for us, and it did work also.
Okay. And then, yeah, so Matt has the question. Can you speak about the testing that you did and why you chose those tests? I guess probably both in terms of the like FEA and CFD analyses, and then any physical testing with actual hardware.
All right. So I would like to hand over this question to Yuvraj for basically the testing of ground systems involve pyrotechnics, and then later on to Sai or Anish, who can tell you about CFD, and then we'll round back to me for the static, structural, and the thermal analysis.
Sounds good.
Hello, am I audible?
Yeah.
Yep, you're good.
Yeah. So first thing that Avinav mentioned was the igniter testings and all, the ground tests. Since we're using a COTS motor as such for the current rocket, we aren't really deploying that system. However, the electronics for that will help us further going on. But we have deployed that system in the recovery charge, basically. The piston and the black powder situation that we have in the recovery bay is by proxy been tested on the ground separately outside the rocket. With regards to the FEA testing, so I am responsible for the payload. So majorly we did modal analysis for our payload, since we wanted to know what would the vibration response be of our 3U CubeSat. And our logic was that we wanted a structure that was weight efficient, that did not violate the guidelines, and also did not dampen any vibrations that we wanted to reach to our experiments, to our sensors, whatever it may be. So we preferred FEA here again because it was in the design phase, and one of the goals for the payload in our rocket is to actually identify what the vibration profile is going to be. So at this point, it was unknown. That's why we preferred to use FEA for simulation of the payload. I guess Anish can continue further.
Yeah, so I'll take over. So we performed CFD analysis over the rocket. Our rocket's max speed was noted to be 0.8 according to the ORKV design. So we performed simulations right from 0 to about 300 meter per second. And we observed that there were no regions of air where the speed was reaching Mach 1. There was no sonic region or supersonic region near the fins. So that gave us a assurance that there would not be any undue pressure gradient acting on the fins. So on the basis of the force acting on the whole rocket and on the fins, especially on the fins separately, we again handed it back to Avinav to handle the structural simulations. So Avinav.
Yeah, all right, thank you. Like first, I would like to answer the question in the chat, like why we chose the tests we did. It was primarily conducted on the basis of what could go wrong, and the tests which were viable to us in this unfortunate situation we have here. We could not actually have access to our workshop, and we could not gather the entire team around together to work for like almost an entire year and a half. So that's one limitation we had, and the other is whatever we could test, we did test. And as far as other potential physical testing options, some of them were actually tested during the 18 and 19 SA Cups, and we haven't really changed the systems much. So we thought that it was okay for us to omit all those tests which have already been done, because we didn't really change the methods of manufacturing of the body tubes and all when we shifted to glass fiber to carbon fiber from glass fiber. And regarding static tests, starting from the top, we have the FEA analysis first of the nose cone bulkhead. Then we have FEA analysis of the nose cone recovery piston and the piston bulkhead that supports the cylinder. Then further down that, we have the payload, as Yuvraj mentioned. Then for the motor bay, we have separate tests for the dampener, the thrust plate, the stringers, and the centering rings. Due to, again, FEA limitations and the amount of meshing and the size the model was, we could not really do it on our laptops, and we didn't have really any access to any FEA labs. So we try to make the best of the situation and do all of those FEA analysis. And apart from that, practical testing, which we have conducted previously, are one is the compression test of our body tubes, and then we have a small scale fin shear test, which really isn't that well documented. So we chose not to put it in the design report. Does that answer your question, or you have any further queries?
I think that answers all of my questions. Matt, if you have anything else, unless you have anything else, I think fin shear test.
The small scale fin shear test was actually a success, but it wasn't fair enough to scale that to the larger model. So we did rely mainly on the FEA results that we got, which we have also put in our design report. It was an explicit test with a drop velocity of 5 meters, which is basically the descent velocity without rope shoot, not the main shoot. So in that FEA test, it was successful, and the small scale shear test, the retention we did not check. We checked the bolt failure, and the bolt failure was not there. So props for that, I guess. But we did try to make the best of the situation, so can't really complain.
Okay. All right.